Thank you for the invitation. I'm just can you see my slide?
We can, yes, perfect. Thank you.
Perfect. Okay. So the outline of my talk is shown here. So I will start with a little bit of background about what Mendelian randomization is, and then I will move on to present this subcategory of Mendelian randomization called two-sample Mendelian randomization, which is really what seems to be the driving force behind this explosion in MR papers, in Mendelian randomization papers that we are seeing in the literature. And I will end by discussing a little bit about what editors and peer reviewers might be able to do about this. And in the end, I was hoping that we would have a discussion, or people would join in with their thoughts. And yes, if anything is unclear, or you have anything during the talk, please interrupt me or raise your hand. So yeah, so this two-sample Mendelian randomization, this is really the method that is driving this flood of papers in the literature. I will come back to that. So a little bit about Mendelian randomization. What is it, and why was it needed? Why was it invented in the first place? So the problem was an issue that became more and more apparent through the 1990s and early 2000s, and that was that conventional epidemiology, which we term observational epidemiology, was found to be able to produce very robust and reproducible associations, but many of these turned out to be non-causal. And what I mean by that is that when they were tested in a randomized controlled trial, where half of the participants are giving a placebo and the other half are giving a drug, it was again and again found that these hypotheses that were raised from observational epidemiology turned out to be non-causal when put to the test. And let me just see if I can get a... Can you see my pointer?
Yes, we can.
Excellent. Okay, so this is just one of a classical example of vitamin C and heart disease, where you have the risk of heart disease on the x-axis, and when you're moving to the left, means a lower risk. And these results from the EPIC studies, these are from observational epidemiology. You can see both in men and in women, the data suggested a strong protective effect of getting vitamin C on heart disease, but when this was retested in a randomized controlled trial, it yielded a null effect. So the confidence interval is over the one line, and actually the point estimate is suggestive of a harmful effect. So completely the opposite of what was suggested in the observational epidemiology. And this same phenomenon was seen for several other biomarkers or factors that were suggested in observational epidemiology to have a really protective effect against heart disease, and then turned out to be null when put to the real test in a randomized trial. So this is another high-profile example of vitamin E supplement and risk of coronary heart disease. So here we have two epidemiological studies that suggested a substantial benefit in taking vitamin E supplements. And you also see these were published in extremely competitive journals, received a lot of attention, and directly led to these randomized control trials. And here 10 years later, this is a meta-analysis of the results from these randomized trials, and you can see absolutely zero effect of taking vitamin E supplement when you and controlling for other factors, so in a placebo-controlled setting. And the culprit, or the problem with these epidemiological associations, even though they seemed extremely strong, is that it was not possible that they were still influenced by residual confounding. So a confounder is a factor that associates both with the exposure and with the outcome, and this can lead to spurious associations or non-causal associations between the exposure and the outcome. And what was probably not appreciated, or in many cases still is not, is that confounding can be very difficult, or even impossible, probably impossible to fully account for by statistical methods. And the reasons for this is that we can only adjust for what we can measure. Many things are unknown, so they're simply not measured. And other things that we do know about are measured with error, or only measured at one time. So we cannot fully statistically account for confounders. So Mendelian randomization was invented as a new method to try to circumvent confounding. And the underlying idea is that instead of looking at exposures, for example, cholesterol levels or blood pressure, then you look at genetic variants that influence this exposure. And the underlying idea is that genetic variation is much less likely to be influenced by these typical confounders that otherwise can affect exposures. And this has to do with the fact that genetic variants are inherited at random from parents. So in a sense, it can be viewed as a randomized exposure. For example, if you have a genetic variant that influences your cholesterol levels, it's very unlikely that your level of physical activity or other behavioral factors can influence that, can associate with that genetic variant. Another assumption that underlies this Mendelian randomization concept is that to be able to use this genetic variant as a proxy for the exposure, the variant must not have an effect on the outcome that circumvents the exposure. So, but if we can find genetic variation that influences the exposure of interest, and we can show that the same variant associates with the outcome, that strengthens the belief that the exposure itself is causally associated with the outcome. So this is the basic idea underlying Mendelian randomization. Yeah, so if we can establish this link from the genetic variation through the exposure to the outcome, that is a much stronger piece of evidence in favor of causality than just looking at the exposure and the outcome association, because confounding is much less likely. And I have a few examples from the early years of Mendelian randomization, some well-known. The first is LDL cholesterol and myocardial infarction. LDL cholesterol is low-density lipoprotein cholesterol. This is commonly known as the bad cholesterol. This is the type that builds up in arterial walls and causes atherosclerosis. So in this scenario, we were interested in studying whether LDL cholesterol was associated with myocardial infarction. And we know that diet influences LDL cholesterol. So this is a potential confounder. There could also be other confounders, but in this example, I just chose diet. But if we are able to find genetic variants that associate with LDL cholesterol, we can use these as proxies instead of LDL cholesterol. And the genotype of an individual, of course, cannot be influenced by whatever that individual eats. So we have removed this confounding factor here. And as I mentioned before, we also have to make sure that these genetic variants don't associate with other factors that could influence myocardial infarction. We can test for that. They are not associated with body mass index or smoking or hypertension. And if this is fulfilled, then we can do the Mendelian randomization study using the genetic variants instead of LDL to test for association with myocardial infarction. These are the results of one of these studies in 2012, where we have the risk of myocardial infarction per 1 standard deviation higher LDL cholesterol. And going up is higher risk. And you can see that from the epidemiological studies was suggested that the risk would be increased. And this is also what we find for this genetically proxied, modeled increase in LDL cholesterol. So the genetics agree with the conventional epidemiology for LDL cholesterol. One thing that's worth pointing out is that the effect of the genetically determined increase in LDL cholesterol appears to be slightly larger than the epidemiological effect. And this is explained by the fact that genetic effects are lifelong. So this means that the cumulative effect on LDL cholesterol in this case is something that has taken place throughout their lives. And so this reflects in a larger risk increase. We see the same when you compare the genetic effects with what we see from trials of LDL lowering cholesterol. So these are statins or PCSK9 inhibitors. And we have on the lower slope, and the slope up here is the effect for the genetic variants, the genetic studies that model the same targets. And now, of course, LDL cholesterol has been known since the 80s to be a causal factor in coronary artery disease. So in this example, the Mendelian randomization studies were more of a confirmatory nature. We already knew that LDL cholesterol was causal. But another factor, or another lipoprotein that has received a tremendous amount of interest is high-density lipoprotein cholesterol, HDL cholesterol. And this has been thought to be a good form of cholesterol. And the hypothesis is that this HDL cholesterol can go into the arterial wall and pull out the cholesterol that built up in plaques. So HDL used to be called the good cholesterol. And the reason it was caused this was when you looked epidemiologically, HDL was extremely strongly associated inversely with the risk of coronary artery disease. This is seen here. So if you have low HDL cholesterol, you have a much higher risk of coronary artery disease. And this is only adjusted for age and gender in the orange. And even when you adjust for additional risk factor, you cannot remove this association. Extremely strong, and could be found in many different epidemiological studies. So this prompted the pharmaceutical industry to try to raise HDL cholesterol, and literally billions of dollars have been spent on this. When we look into the Mendelian randomization of HDL cholesterol, so here we have the risk reduction that epidemiology suggests, a strong risk reduction per 1 standard deviation higher HDL, but the genetics suggested that there was no protection. And this was actually also what was found in these huge randomized trials that cost, as I said, billions of dollars, that came out coinciding with these first genetic data. This is from the Lancet 2012, and if we had known this before starting these trials, it might have changed the way that these resources were spent. And this is just again to compare with how it looked for LDL cholesterol. Here the genetics agreed with the epidemiology. So this is the basic idea behind Mendelian randomization, to use genetics as a proxy for an exposure of interest. And the big success stories from the last decade have really been these lipoprotein and associations and other circulating biomarkers association with atherosclerosis, where Mendelian randomization has confirmed causal factors like LDL cholesterol and also refuted other factors like HDL cholesterol and C-reactive protein and other circulating factors that had been drug targets before and have turned out not to be causal. So moving on, where do we find these genetic variants that associate with the exposures and outcomes of interest? So marked with this question mark here, and also the one that goes through from the genetic variants to the outcome. So this has become increasingly easy to do due to this explosion of genome-wide association studies, large-scale genome-wide association studies. And now I will move on to talk a little bit about two-sample Mendelian randomization. This is a subtype of Mendelian randomization. And how two-sample Mendelian randomization is a method, a Mendelian randomization method, where we use summary statistics, so results from already performed genome-wide association studies, to do a Mendelian randomization study. So just using this framework again, we fetch the results of the genetic association with exposure from a GWAS. It could be, for example, in this example, I just used the UK Biobank, and then we find the genetic association with the outcome also from a GWAS, from a genome-wide association study. And it could be the same cohort and could also be another. So now here I just used to show the large cohort from the US Million Veteran Program. So two-sample Mendelian randomization is based on results from GWASs that have already been run. And it's important to point out here that now there are thousands of genome-wide association studies available. All the traits in these large-scale studies, like UK Biobank and the FinGen study, Million Veteran Program, they have been GWASed. And the results are publicly available. They are shared online in databases. And I've shown two examples here. This is a GWAS catalog where you can go in and search for outcomes of interest, traits of interest. They have almost 100,000 data sets that you can browse through there, and this is free. Anyone can download it. This on the right is it came online just a few weeks ago. These are results of a meta-analysis from FinGen, the Million Veteran Program, and UK Biobank. So these are 3 of the largest cohorts in the world. And you can see, for example, type 2 diabetes, 339,000 cases and 1.2 million controls. So massive sample size where you can get these GWAS data. And these summary results have also been collated into databases that are specifically tailored to run Mendelian randomization analysis. And here I've again shown 2 of the ones that are being used for thousands of these types of studies. The one is MR-Base, which was done by George David Smith and his group from Bristol, and where you can run these analyses with a few clicks of the mouse based on GWAS results in their database. And another similar database made by the same group is this Open GWAS project, where you can run similar analysis online. You can also easily download these GWAS summary results to your own computer and analyze them with user-friendly R packages that make this really, really straightforward. This is one of these packages that a lot of people use. It's 2-sample MR. You can go in and read the documentation, and this is just an example of how clean and few lines of code you actually have to put in. And one of my students just let me know before here you can actually skip the first line, so it's just the last 4 that you need to run. So you define your exposure, you just define your outcome, and then it takes care of the rest and spits out Mendelian randomization results. And this is just an example from their documentation of how to run these analyses, where they take you through it step by step. And as I mentioned before, it's a really clean, few lines of R code, and they even provide sensitivity analysis that make it easy to do these extra analysis that are required for in modern Mendelian randomization studies. This R package produces really excellent figures, like publication quality figures, that you can also adapt or continue working on in an R environment. These are based on this ggplot code. If anyone working with R will be familiar with ggplot. These are just 2 examples of the type of figures that the code spits out, where you can see different MR methods, regression lines, and the points for the individual genetic variants that was put in, the effect on the exposure on the x-axis, and the effect on the outcome on the y-axis. So here it's body mass index versus coronary heart disease. And similarly, publication quality sensitivity analysis. This is just one example of one of these leave one out analysis that gets produced. So the advantage of this 2-sample Mendelian randomization are that it has really democratized the ability to run Mendelian randomization, and spread this method also to non-experts. And this is a huge advantage. This means that basic researchers can actually run these analyses and add them as an extra tool to for example, basic research. Another advantage is that the methods are being harmonized, and the way that the data sets are being cleaned and transformed before entering into the models also harmonized. So this reduces the overall, will reduce the risk of errors, simply just because the code and the pipeline that's being run is being handled centrally and identically. However, there are also some problems, and this is what the rest of this talk is going to center around. And there are at least two big issues here. The first is that naive use of this kind of data can easily produce meaningless or even wrong results. And I have a few examples of that. And an equally or perhaps larger problem is that this ease of access can facilitate mass production of results. And this is something that is very clearly now being misused by researchers, and we suspect also paper mills. So first, a little bit about the naive use of this type of data. So one important assumption for interpreting Mendelian randomization is that the change in the exposure that we see due to these genetic variants, it should be similar to the effect that you would get by changing the phenotype by some behavior. And here we have, as an example, body mass index. So if we find in our Mendelian randomization study that genetic variants that associate with higher body mass index, they associate with for example, increased risk of diabetes. You would, in a Mendelian randomization framework, the gene equivalence statement means that if you change your body mass index, you would expect to see this the same as indicated by the genetic association. So here, if you lower your BMI, you would expect to see a lower risk of type 2 diabetes. But where you need some biological interpretation and understanding. So for example, if you were to lower your body mass index by lowering your calorie intake, then you could reasonably expect that this would also protect against type 2 diabetes. And this has to do with the way that genetic variants influence body mass index is probably to a large extent via your calorie intake or how much you eat. The same could be said about physical activity. But this is a little bit of an absurd example. But if you consider an adult, you knew nothing about biology, and if you lose a leg, your body mass index is lowered substantially. But it would be very naive to think that would protect you against type 2 diabetes, right? So this is a little bit of a silly example. But if you imagine we knew nothing about biology, this type of misconceptions or misinterpretations could could arise. And a similar scenario, maybe even more complicated, is with smoking, where we know that smoking causes lower body mass index, but you probably wouldn't recommend anyone to smoke to lower their risk of type 2 diabetes. So the point I'm trying to get to here is that to be able to interpret Mendelian randomization, you have to have some biological insights, and you have to justify that the genetic effects can be recapitulated by a behavioral effect or a change in the phenotypic environment. And that would produce the same effect on the outcome as for the genetic variant. And one thing that really complicates or is actually modeled or made it more difficult is that these new genetic association studies, they're becoming so large that the power is enormous. So we can pick up tiny effects. This is an example of this type 2 diabetes genome-wide association study I showed before. When you have 300,000 cases, you see almost there's an association everywhere, basically, hundreds and hundreds. Many of these will be tiny. This can make it very difficult to interpret what actually goes on from the genetic variant down to the outcome. You can imagine many different ways that a genetic variant could end up influencing type 2 diabetes, and some maybe work through pathways that we cannot even imagine, like behavior that can make it difficult to interpret. And if you look into these things that have been measured, many of them are, really it becomes difficult to think about what actually causes these changes. So, for example, there's a lot of dietary intake. So they've run genome-wide association study of cheese, blue cheese intake. You can find genetic variants that influence that. Chocolate intake, bacon intake, and there it gets really tangled and difficult to get a grasp on what's driving this association. And it's probably not reasonable to think that changing your blue cheese intake when you are 50 corresponds to the effect of a genetic variant that associates with a slightly different change in blue cheese intake throughout life, because the genetic variant could have influenced that blue cheese intake via many ways that we cannot think about. It may not be recapitulated by just changing that during adulthood. Same with television, another example. You can find many of these types of nonsensical results if you go and look at Mendelian randomization studies. This is just from this week. I did a quick search where the researchers tested whether COVID impact QT interval prolongation. So this is measured by ECG. And the problem here is that, so COVID, of course, appeared in 2020, but these ECGs, they were measured in 2015. So I mean, it doesn't make any sense. Like that COVID would have to have traveled back in time to influence these QT interval measurements. And this was just one example that quickly popped up by searching today. So this was the one part of these potential problems. The other is that two-sample Mendelian randomization, because it's so easy and all the results are publicly available, it facilitates mass production of results. And this is a PubMed search for Mendelian randomization. and stratified by year. So for 2008 up to 2024, and the number per year on the y-axis. You can see the first years. So Mendelian randomization was really was first introduced in the mid-2000s, and in the first few years, maybe about 100 every year. And then here in the last few years, it's really taken off in an exponential manner. And we wrote this comment a few months ago and projected that this would be the end for 2024, that it would end about 5,000, that we would reach 5,000 by the end of 2024. But I just redid this and realized that I've been much too conservative. Actually, what we're ending up on in 2024 is actually 6,000 Mendelian randomization papers. So this is truly an exponential increase, a doubling every year. So you can do a little math, and if this continues, then in 6 or 7 years, all papers in PubMed would be Mendelian randomization papers. I mean, we would reach a million every year. Of course, this is not going to happen, but it's just to show the scale of this explosion is enormous. And then the obvious question: what's driving this exponential increase? And we don't know. We have some ideas. So we can say that almost 100% of this increase is due to papers coming from Chinese researchers. And the vast majority of these papers are two-sample Mendelian randomization papers. So based on these summary statistics and pipelines that can quickly be run. And this is something that we don't have data on, but I definitely have an impression that many of these papers are being written or done by ChatGPT or some other large language model. Thinking about this, I decided to put this to a test and just can these tools, can they write a two-sample Mendelian randomization paper? So I tried to do this and gave it a really, this is Gemini, this Google's ChatGPT version or large language model. So, and I gave it this very small, like simple prompt: please write a two-sample Mendelian randomization research paper of noodle intake on educational attainment. So of course this is ridiculous, right? But I gave it the result estimate and then it starts writing, and it's actually pretty convincing. It even puts in a sensitivity analysis, giving the right tests to use, and supported the robustness of these primary findings, and the introduction is quite good. It goes on describing the study design, even goes so far as say, well, you use the UK Biobank and summary statistics for genome association studies. The methods are described in more or less the correct way, and goes on to the discussion here, compelling evidence for causal link between noodle intake and educational attainment. And so the short story here is that yes, especially if you consider adding some of these automatically generated publication quality figures, this is actually quite close to the kind of papers that are being sent for review, at least that I receive a lot of these papers as a peer reviewer. And in my opinion, this type of study could easily pass review and be published. So moving on to the last part. So in the face of this flood of two-sample Mendelian randomization papers, is there anything that we can do? And so earlier this year, there was a bunch of comments and editorials and papers from people in the Mendelian randomization field, really sounding the alarm. And I was co-author on one of these, reclaiming Mendelian randomization from the deluge of papers and misleading findings. And George David Smith was a senior author, also put this out on Twitter, and where more people see it. Other colleagues published similar commentaries at the same time. So this is from Stephen Burgess and his colleagues, and George Davy Smith with his colleagues also simultaneously published 3 identical editorials in these tobacco-related journals. And our recommendations, so one recommendation is to simply, this is a recommendation for editors, is that to desk reject papers that only report two-sample Mendelian randomization results. And the rationale behind this recommendation is that all two-sample Mendelian randomization studies based on publicly available GWAS, they can be browsed online with a few clicks of the mouse, and they can be done in R using just a few lines of code. So in essence, they can be viewed as already published, and in any case, they are so quick to redo that the value of putting them into a scientific paper and publishing it is hard to see. It is comparable to Googling to get these type of results. Another recommendation is for editors is that the author should provide these checklists, and these are similar to what is seen in other, for example, in meta-analysis or randomized trials, where you have to go through these checklists to show if you've gone through the proper steps. This has also been developed for Mendelian randomization now, with this list of things, and this should be sent with the paper when it's being submitted. And the final recommendation is that these gene environment equivalents, they should be justified. So there should be some biological interpretation and discussion going into these papers, and not just blindly running associations of genetic association versus another genetic association. So just to reiterate, biological insights necessary to conduct and interpret Mendelian randomization studies. And the problem for the pessimistic view on this is that it might be all well and good that we come with these recommendations, but it is really in some ways an arms race, where the authors of these mass-produced two-sample Mendelian randomization papers, they just adapt. And I've already now experienced that they're starting to send in these strobe MR checklists. And I also have a feeling that these large language models, they're getting so good that they can actually add something like biological interpretation that are seemingly sensical, or could be imagined to fool many reviewers and editors. For peer reviewers that receive these papers, and this is actually a huge burden for many in the Mendelian randomization field, we receive numerous requests every week. So here we provide a template for rejection, so that they can just quickly inform the editors of this issue and get the review off their desk. We provided this peer review template in our comment earlier this autumn. Another thought or hypothesis is that it might AI tools help editors to weed out these type of automatically generated two-sample Mendelian randomization paper. So again, this I wouldn't be overly optimistic. This is sort of back to this arms race scenario, but it seems that then we are just ramping up once more. And I will just share one sort of dystopian experience I had recently with the two-sample Mendelian randomization. So basically, I reviewed one of these papers, obviously written by ChatGPT, so I summarily recommend the rejection. But then reviewer 2 was super positive and recommended acceptance. But at the same time, it was clearly 100% done by ChatGPT or something similar. You start to recognize the way it writes its reviews. So we're sort of veering into the absurd scenario where the author, the paper is written by AI, the review is done by AI, and if the editor is also done by AI, I mean, yeah, it starts to get dystopian, right? And just to end up on another thought here is that, so now I've talked a lot about two-sample Mendelian randomization because this is what we have identified as an issue now. It is very obvious. But there are likely other similar exponential increases in other types of mass-produced papers that are already starting to flood the literature or will be here in a short while. One thing that I've noticed, I get a lot of invitations to review papers coming from this National Health and Nutrition Examination Survey, and this is a publicly available data set from the US where you can do observational epidemiology. So this is not Mendelian randomization, but it's just it's free, easily accessible. And if you look at PubMed search of the acronym for this study, it follows a normal development here, and then in 2023 it was 4,900, and then it took a huge jump up in 2024, jumping more than 2,000 already. And my suspicion is that this is basically all this increase is driven by mass-produced papers, similar to what we saw for the two-sample Mendelian randomization. And this seems to really be an exponential increase there. This was what I had. I'll be happy to answer anything or hear your thoughts if you've been exposed to two-sample Mendelian randomization, what your thoughts on it are. I will just try to go so we can see the screen.